All right, if we can do 2 and 3 and 4, can we do 5? And the answer is yeah, but who wants to? If we've got 5 input variables, we're talking about 32 minterms. We need some kind of weird grid with 32 cells in it, and we got to figure out a gray code numbering that works. I don't know. I don't even know what that looks like. In this class, I will ask you to use Carnot maps up to 4 input variables. We will not treat 5 or higher. Anything more than that, and we're going to try to find some sort of software that'll do it for us. So what's next? Sum of minterms isn't the only representation we have in canonical form. There's also product of max terms. Can we use kmaps to simplify these? The answer is yes. Because remember that the complement of a function in product of max terms form is very closely related to a function, some function, in sum of minterms form. Let me remind you what I'm talking about. If f is written this way, f complement is written this way. Remember? And the reason for that is that minterm 0 looks, this is 3 variables, by the way, x, y, z. Minterm 0, all the literals are complemented. Max term 0, none of the literals are complemented. And that difference means that we can take the complement just by using the same numbered minterms of the max terms that form the original expression. Okay, so f complement is this. And we know how to simplify this. Three variables. Zero, 1, 3, 4, 5, 7, 6. Okay. That's f complement. Because that's sum of minterms. So if that's f complement, where is f? F lives in the zeros of f complement. Right? If a thing is expressed in these 5 minterms, how many minterms are not part of this function? 3. Those 3. But the minterms that aren't part of this function are the complement of that function. It's everything not this function. The stuff in green is already the complement of f. So the zeros of the complement represent the function itself. If we were given a Boolean function in product of max terms form, same numbering, 0, 1, 3, 5, 6. And we simplify the zeros. We simplify the blank squares because that's really where the function lives. It doesn't really permit a great simplification, there aren't any cells adjacent to it, and that's what happens when I just make up functions off the top of my head. But 1, 2, 3 terms. 3 terms is all we need to write this function. Remember, these are min terms, so we end up expressing this function as this, I'll use a different color. We end up expressing this function f, which we've represented here with the zeros of the complement of f, which seems a little bit redundant, but it works. If this is x, y, z, so here we go, x, x, y, z, so we're talking about x, not y, not z. We're talking about x, y, z. And we're talking about not x, y, not z. And we're done. Now, these are min terms. If there had been some simplification, then we would have gotten a better result. So, all right, let's try a better simplification. What if I change that to 7? 0, 1, 3, 5, 7. 0, 1, 3, 5, 7. So instead of 6, we've got a 1 there. I'll use green. And the 0 in the complement lives here. And now we can see all kinds of cool simplifications. We've got 2 adjacent cell partners. So we've got a region here and a region here. So we're talking about x, not z, and y, not z. Cool. So we can use the zeros of a product of max terms expression to simplify the function. Once we're here, we can figure out how to write that as a product of sums if we really want to. In fact, it's actually kind of already there. We can factor out the z complement. We've got x or y. So there's a sum, and z prime is its product of sums form right now. Cool deal. Okay, next segment.